The first thing you must understand is that the composition of stars, the abundance of their various chemical elements, is not that different from one star to another, and this is true everywhere in the universe. There are some differences. There are essentially two classes in terms of abundance. We call them population 1 and population 2 stars, and I will describe this in detail in a future chapter. But let's take all the population 2 stars, like the Sun, which is essentially the majority of the stars in the universe. They have very similar composition. And so the differences in the spectral lines, why are some elements display very dark, very broad spectral lines, and other elements are very faint, is a function of temperature. So we take a star like a Sun, which is a G2 in its spectral class. It has a relatively strong hydrogen lines and very strong metal lines. Metals are all the elements heavier than helium. In astrophysics, anything heavier than helium, well, we call it metal. So, if we compare this to an A0 class star, so 10,000 Kelvin on the surface, you can see that the hydrogen is much stronger than the Sun. This star doesn't have more hydrogen than the Sun. It's simply that the absorption of light by hydrogen atoms, by electrons in the hydrogen atoms, is happening more often. So there are stronger absorption lines. And you can see that there is a strong presence of helium, which is barely visible in the Sun. So to understand why this is the case, think about the Bohr model of an atom. So think about some arbitrary element and think about all the energy levels that the electron can occupy in that element. So this is not necessarily hydrogen, and in fact the energy levels are a bit more complex than hydrogen for the other elements. But essentially you have the ground state, which is the default energy level when the atoms are cold, when the temperature is cold. The population of electrons in a gas occupies the ground states. So all the electrons are in the ground state. When photons travel towards the atom, so black body radiation from the surface of the star, radiation comes out of the star, passes through the atmosphere of the star, which is populated by atoms, hydrogen, helium, etc. So if the star is extremely cold, the population of electrons is in the ground state. So the population of electrons, these electrons in the various atoms, will be able to absorb only the photons that allow them to jump to higher energy levels. And generally, out of the ground states, the jumps are pretty large, so the energies required are large, which translates into absorption of ultraviolet radiation. When you increase the temperature of a gas, you're making more collisions. What it means is that for the population of the electrons, there will be a distribution across the excited states. So some electrons will be populating these higher energy levels because they gained energy from the collisions with other atoms, not by absorption, but by collision. The higher is the temperature, the bigger is the higher is the distribution in those levels. So if we take hydrogen, the temperature close to 10,000 Kelvin is when a larger percentage of hydrogen atom will have their electrons populating the second energy level or the first excited state, n equal 2. Now, why is this important? Because in order to absorb visible light, you need to make the right jumps. The energy gained by the photon corresponds to the energy difference between levels, right? And generally speaking, the higher is the excited states, the closer are the levels to each other, smaller is the jump, and the smaller is the energy of the photon required. So if you start from a lower level, you need big jumps, which means you need ultraviolet. If you're populating very high energy levels, you need small jumps, which translates into infrared. So there is only a region of intermediate energy levels. For hydrogen, that has to be n equal 2. But if we take a different element, n can be 3, 4, 5, could even be multiple levels. Doesn't really matter the specifics of each element. What we know is that as you increase the temperature of the gas, more and more electrons will populate higher energy levels. And then there are some energy levels where absorption of visible light photons is possible. And visible light photons will enable you to jump to higher energy levels. So for hydrogen, you can only absorb a visible photon if you are at the second energy level. On the first energy level, it's the Lyman series, you need ultraviolet. After second, so starting with third, the jumps are so small that you're basically only absorbing infrared. So for helium, for carbon, the level that you need in order to be able to absorb visible light is not necessarily n equal 2, when I don't know what it is, and it doesn't matter, but there is a key energy level that the electrons have to be in, and in order to start at that key energy level, the temperature must reach a certain point. If the temperature is too low, more electrons will be populating lower energy levels because not enough collisions, and so absorption of ultraviolet is what is required. If you go too far, if you increase the temperature too much, then more electrons will be populating higher energy levels and fewer of them will be populating the key energy level. So more electrons statistically will be occupying these higher levels, or maybe even ionized. So you have fewer atoms, fewer neutral atoms available to absorb light. And so when the temperature is high, the electrons are absorbing infrared, or they're not even there. When the temperature is too low, they're absorbing ultraviolet, but only when you reach that key temperature where the larger fraction of electrons are in that key energy level, you will be absorbing visible light photons, and therefore you will be seen as you will see strong absorption lines because the spectrum of absorption lines is in the visual part of the electromagnetic spectrum. Anything ultraviolet or infrared that is happening, we do not see. We're only looking at the visible part of the spectrum. So, for a star like the Sun, metal, both ionized and neutral, are so elements of those metals, so carbon, oxygen. There is a larger fraction of atoms whose electrons are in the key level, so they are able to absorb visible light photons. The jumps are just right for absorbing visible light photons. While for stars like the Sun, the temperature is very low for hydrogen, so a bigger fraction of hydrogen atoms are in their ground state, and a smaller fraction is in the energy level n equal 2. So there won't be as many jumps starting with level 2. There will be more jumps starting with level 1, which is ultraviolet. If the temperature is too high, so we look at B class stars, you see how the metals become very faint, because the metals which have valence electrons, very volatile, I guess, will be very excited or ionized too much. So there won't be anything left to absorb visible light. And the same thing for hydrogen. Hydrogen decreases dramatically in these regions. So we're looking at 20,000 to 30,000 Kelvin stars. A lot of the hydrogen atoms will be very excited or ionized. Not many electrons will be left in the level n equal 2, so not many hydrogen atoms will be able to absorb visible light. But at that point, helium becomes very strong because it is difficult to bring helium to its key critical level, because I'm assuming the jumps here is very big. You need much more violent collisions for that to happen. So this is the idea behind the wide range of spectral classes that we see. It's all a matter of having the electrons at the right level to absorb visible light, and in order to do that, you need to have the right temperature.